everyone. Welcome to this session. Next, my colleague Rajesh and me, Jeff, will give you a presentation about Apache Tez, its present and future. So, how many of you have heard of Tez? If you have, please raise your hand. Oh, thanks. Surprised me, yeah. So, I think that many of you must know Pig, Hive, and Cascading, and many of you may already use these tools in your routine work. And that means you have already used Tez unknowingly. So this presentation will tell you what is Tez and how to use Tez to make your routine work more efficiently. Now here, this is today's agenda. I will cover the first two sections, Tez introduction and its feature deep dive. And my colleague Rajesh will cover the next two sections. So first, I will give you one simple example to make a comparison between the MapReduce and the Tez. So here we have one Hive query. You may know that by default, this Hive query will be translated to several MapReduce jobs. So you can see that in the, on the right side, we have four circles, which means 4 MapReduce jobs. And each MapReduce job will write data on the HDFS, and this data will be read by the next MapReduce job. Now let's see how Tez implements this Hive query. On the right side, we can see that one circle, which means it only requires one job. And there's no intermediate data written to the HDFS. Instead, each vertex will port data from its upstream vertex. So this is just one simple comparison between the MapReduce and the Tez. Just want to give you one simple impression of what is Tez. Of course, Tez has a lot of other features and improvements compared to MapReduce. I will cover them later. So first, what is Tez? Tez is a distributed execution engine framework. Here, I want to emphasize that Tez is a distributed execution engine framework. It's not an execution engine. So that means you can use Tez to build the execution engine for your specific purpose. Next, Tez try to express the computation as the data flow graph. Also, you can call it DAG. And third, Tez is designed to be highly customized to meet a broader spectrum of user cases. You can use Tez for ETL, for interactive query, and for machine learning. And you can only run Tez on Hadoop 2, because Tez is built on top of Yarn, the resource management framework of Hadoop. And the last Tez is the open source Apache project. Tez is started around 2 years ago, and around 1 year ago, it became the Apache top level project. Just now I mentioned that Tez try to express the computation by DAG. So what is DAG and why DAG? DAG means direct acyclic graph. First, it is a graph, and it is directed with no circle. Actually, most of the work in the data area can be modeled as a DAG, and any complicated DAG can be composed of the following 3 basic paradigms: sequential, merge, and divide. So sequential means that we have one data set and we'd like to transfer it from one kind of format to another kind of format. For example, the projection filter group by. The second paradigm merge means that we have multiple data sets and we'd like to merge them by some rules. For example, the join, union, or intersect. The last paradigm is divide, which means we have one data set and we'd like to divide it into multiple data sets. For example, the split operation in Pig. So now let's see how to express DAG in Tez API. Tez has two APIs for that. One is the DAG API, the other is the runtime API. The DAG API allows the user to build a DAG, which represents the topological structure of the data computation flow. And the runtime API help you to specify the application logic of each computation unit, and it can help to specify how to move, read, and write the data between these vertices. Now let's first see the DAG API. There's two main components in the DAG API. One is the vertex, the other is the edge. So when you create the vertex, you can specify the processor, parallelism, resource, and etc. So when you create the edge, you can also specify lots of properties. So here, I list the most important one, the data movement. For Tez, it supports 4 kinds of data movement: the scatter-gather, broadcast, one-to-one, and custom. So the scatter-gather is very similar to the shuffle of MapReduce. As we know that the shuffle will involve several steps. You need first partition the data on the map side and sort merge the data on the reduce side. Usually, the scatter-gather is used in group by join. And we know that sometimes we don't need to partition sort merge data. So that's the reason why Tez introduced other kinds of data movement. For example, the broadcast will be used in pick replicate join and high broadcast join, in which case we have one small data set and we'd like to join this small data set with a very large data set. The other data movement type is the one-to-one. This will be used pick order by. I will cover it later. So if neither of these 3 data movement types don't fit for your requirement, you can also implement your own data movement type. We can call it custom. So now let's see the runtime API. For the runtime API, there's 3 main components: the input, processor, and output. We can also call it IPO model. So the input is the data that the process will receive. And for Tez, each vertex can have multiple inputs. This is the advantage compared to MapReduce, as we know that one MapReduce job can only have one input format. And the next thing is the processor. Processor has the application logic to consume your data and produce the output. The next thing is the output. The output is the data that you will write on the edge. And similar as the input, each vertex can have multiple outputs. So here I list several built-in library of input, output, and processor. For example, the MR input can read the data which is compatible to input format, and MR output can write the data to which is compatible to output format. So usually the input-output are paired because one pair of input-output represents the 2 sides of one edge. For example, the ordered group KV input and ordered partition KV output is the one input-output pair of scatter-gather edge. And the unordered KV input and unordered KV output is the input-output pair of broadcast and one-to-one edge. And of course, each application can have its own processor. For example, Pig has a Pig processor and Hive has a Hive processor. Okay, just now I talked about the Tez's biggest feature that tries to express the computation by DAG. So now I will list several benefits of DAG. The first benefit is that it is much easier to express the computation by DAG. So as I just mentioned, that there's 3 basic paradigms, and each complicated DAG can be composed of these three basic paradigms. And if you have any experience in the database, you may know the concept of query plan. So each query will first be translated to a query plan, which will be submitted to the underlying execution engine. And actually, this query plan is the DAG. The next benefit is that there's no intermediate data written to the HDFS. This also means that we will have less pressure on the name node. Because when we read or write data on the HDFS, we have to first query the name node. The next benefit is that there's no resource queuing efforts and less resource contention. And the last benefit is in test, it will be more optimization opportunity with more global context. Because since we model the whole computation as a DAG, so for each vertex, it has the global context. For each vertex, it knows the context of its upstream vertex and its downstream vertex. So for example, in test, it is much easier to take advantage of the data locality. So just now I mentioned that give you a basic introduction of TEZ and talk about its biggest feature about express computation by DAG. Of course, TEZ has also has a lot of other features. So here I will next I will talk about several of the main features. So the first feature I will talk about is the container reuse. Here the container means the young container. As we know that in MapReduce, we have to allocate each container for each task. And after this task is completed, we have to release this container. While in test, we do not need to release that container. We can continue to use that for the next task. So the container reuse will bring lots of benefits. The first benefit is that we can consume less resources. So since we consume less resources, we can reduce the overhead of launching JVM and the overhead of negotiation with the resource manager and the overhead of resource localization. And the next benefit is we can reduce the network I/O. So how is that achieved? For example, we have one container that has already run one task, and this task has its output written to the local disk. And then we reuse this container for another task. And luckily, this task will read the data of the last task. So in this case, we do not need to pull the data through the network. Instead, we can read it from the local disk. So TEZ will encourage such kind of container reuse to take advantage of the data locality. The last benefit is that the object caching. Since multiple tasks can run in the same JVM, so all these tasks can access the same data in this JVM. Okay, the next feature is the test session. As we know that for each MapReduce job, we need to launch one AM. While in test, we can reuse the same for multiple DAGs. That means we can reuse the containers across DAGs, and we can share the data across DAGs. The next feature is the dynamic paradigm estimation. As we know that one job may run on different sizes of data, and for each run, the data distribution may be different. Sometimes it may be even, and sometimes the data distribution may be very skewed. So the parameter number is very critical for the performance. And the test provide a very good feature for you to estimate the parameter number at a long time. The key thing here is the vertex manager. The vertex manager is much like a controller of the vertex. It can listen to other vertex status, coordinate, schedule its task, and also help for communication between these vertices. So now let's see how vertex manager do the dynamic paradigm estimation. On the right side, we can see that there's two vertices. One is the mapper vertex, the other is the reducer vertex. So when the task in the mapper vertex is completed, it will send a message to the vertex manager. And this message contains the data size information. And the vertex manager will determine the right paradigm number of the reducer vertex based on this information. Now the next feature is the ATS integration. Here the ATS means application timeline service. Tez will push its learning data to the ATS. And the data in the ATS is mainly for several purposes. One purpose is for monitoring. Another purpose is for performance analysis. And my colleague Rajesh will talk about these two things later. Now the next feature is the recovery. In Tez, the AM may crash in some corner cases. It may crash due to the auto memory or node failure. So if the AM is crashed, the next AM attempt will be launched automatically. And it will continue from the last checkpoint. And the whole recovery process is transparent to the users. Okay, just now I talk about a lot of Tez features, including the express computation by DAG, container reuse, test session, recovery, ATS integration. So now I will give you one concrete example to show you how Tez uses these features. Here we have one simple pick script, which is order by. You may know that this order by will be translated to two MapReduce jobs. The first MapReduce job is for the histogram calculation. So the next MapReduce job will use the histogram data to build a customized partitioner to repartition the data. So finally, the data will be globally sorted. Now let's see how Tez implements this pick script. On the right side, we can see that there's 4 vertices. The load vertex has 2 outputs. One output is for histogram calculation. Another output is for repartition. And the partition, the vertex partition has 2 inputs. One is the histogram data. The partition vertex will use the histogram data to build a customized partitioner to repartition data. And finally, the data is globally sorted. So let's see what kind of features we use here. The first feature is that we express the computation by DAG. So there's no intermediate data written to the HDFS. The next feature is container reuse. Actually, this feature is used implicitly. Many of the containers used by the vertex loader will be used by the vertex partition, so that it can take advantage of the data locality. Okay, so just I give you an introduction of Tez and its features. Now next, my colleague Rajesh will talk about the remaining 2 parts. Rajesh, please.
Thanks, Jeff. So I'll concentrate mainly on the performance as well as the debuggability aspects. So large clusters can have heterogeneous hardware and a combination of good as well as bad nodes. So the job runtimes can get heavily impacted if the task attempts are scheduled on some of these bad nodes or on a slower set of nodes. So when speculation is enabled, Tez tries to gather the runtime statistics of all the task attempts, and based on this information, it identifies the stragglers which are running a lot more slower than which are running a lot more slower when compared to the other tasks in the same vertex. So based on this information, the speculative attempts are scheduled, and if the speculative attempts finish fast, the original attempts are automatically killed. So this feature will be very useful in the case of large clusters. Tez stores the intermediate data generated in the producer as well as in the consumer side in an IFL format. So just to take an example, in the producer side, be it ordered output or be it unordered output, the data is generated in the IFL format. And in the consumer side, as the data gets pulled from various source tasks, and if there is memory pressure, it will end up spilling the data onto the disk. So at that point in time, IFL format is being used. So a typical record in the IFL format will comprise of the key length, the value length, the key bytes, and the value bytes. However, this may not be the best suited format for all use cases. For instance, if you have a sorted stream of incoming data with duplicate keys, this particular format will end up writing all the duplicate keys again and again. So it's going to bloat up the memory in the sort buffer, as well as the amount of disk space that is required for storing the I file is going to be higher, or it's going to bloat up that particular size as well. In turn, this will also occupy the network bandwidth. The reason is, if you have larger amount of data in the disk, it has to be transferred over to the consumer as well. So it's going to take up a lot of I/O as well. So in the recent versions of Tez, we try to modify this slightly in such a way that it caters to both the use cases that I talked about, which is having unique set of keys as well as having a bunch of keys which have duplicate keys as well. So it starts off by writing the normal IFL record, but the moment it encounters a duplicate key, it writes the RLE marker followed by a bunch of values that are associated with the keys, followed by the value n marker. So you can think of it more like a key comma list of values pattern. So with this, in our internal benchmarks, we observed around 57% memory efficiency and around 23% reduction in the I-file size. Tez, when it serializes the data to memory, it ends up writing the key size as well as the key bytes associated with that. The same thing applies for the value as well. And when it serializes the data from the memory to the disk, it ends up writing the same key size followed by the data which is stored in the memory. So if you look at it, essentially it is wasting 8 bytes of data when writing the data from the memory to the disk. So in the recent versions of Tez, we introduced fast byte serializable, which optimizes this particular use case. It may not sound a big improvement if you are trying to compare or if you are trying to process tens or hundreds of rows, but this will be a big improvement if you are trying to process millions or billions of records. In our experiments, we observed around 25% improvement in the I-file size. And it also reduces the amount of serialization as well as the deserialization cost. It is not uncommon to see containers of size 4 GB or greater than 4 GB in sizes these days. However, the amount of memory that we could allocate to the sort buffer was always limited by 2 GB limit in the earlier versions of Tez. In the recent versions, with the modifications in the pipeline sorter, we are able to allocate greater than 2 GB sort buffer, and this internally means that it will be able to, we are able to reduce the number of spills that will end up happening in the case of large jobs. We also reduced the CPU cost involved in the key comparisons in the pipeline sorter, which will help in the overall runtime of the job. As I mentioned earlier, consumers pull the data from various sources and start merging the data together. So it's quite possible that it's trying to pull all the, it's quite possible that it's pulling the duplicate keys as well from different sources, and we didn't have RLE enabled in the reducer side, in the reducer merge code path. So we enable RLE in the reducer merge code path in the recent versions of Tez, and we saw around 10% improvement. This helps in reducing both the I/O as well as the CPU cost. Just to give an example, in this particular DAG, the reducer number 2 has taken almost 29 million CPU milliseconds, and the entire DAG took almost 691 seconds to execute. With the fix, the same reducer 2 has taken only 22 million CPU milliseconds and 621 seconds to complete the entire DAG. So that's a good improvement in terms of both the overall runtime as well as the CPU utilization. Tez automatically scales down the amount of memory that is allocated to various inputs as well as outputs. So in this particular DAG, you can see that a couple of vertices have got too many number of inputs as well as outputs. So in the older versions of Tez, what used to happen is the amount of memory will be pretty much equally distributed to all the inputs as well as the outputs. But that might not be the best option because you might want to allocate as much memory as possible to the sort buffers because that's where the memory is required, as opposed to the unordered use cases. If you don't allocate that much amount of memory to the enough memory to the sort ordered outputs, then you'll end up having a lot of spills. So in the recent versions of Tez, we introduced the weighted memory distributor with which you can control the amount of memory that is allocated both to the input as well as the output, the various different inputs as well as outputs. So that gives you a fine-grained control on the amount of memory that is allocated. So we saw around 26% improvement in the task runtime in the internal benchmarks. As Jeff pointed out, broadcast is one of the data movements that is supported in Tez, wherein the source generates the data and which is pretty much sent to all the tasks in the downstream vertex. This will not be a problem if you have one source as well as 10 or 100 downstream tasks in the vertex. However, this could become a big issue if there are like 10,000 tasks or like 1,000 tasks in the downstream vertex and they all are trying to pull the data from the same source. So with the fix, what we did was, it is quite possible that many tasks pertaining to the same vertex might be running on the same container. So with the fix, what happens is that the task which gets launched first tries to pull the data from the source, and the subsequent task pertaining to the same vertex running on the same node, they try to check whether the data is locally available or not, and then try to pull it over, as opposed to contacting the source. If it is not available, anyways it will contact the source and then download the data. This drastically reduced the number of TCP connections as well as gave a good improvement in the latency as well. It is common to see data skew in the production jobs. So just to give an example, it's quite possible that 20% of the task might be generating almost 80% of the output. So in this case, even the slow start may not be useful. The reason is, even though the slow start is going to launch all your reduced tasks, unless and until the source task have generated or completed generating the data, the reduced task will not be able to pull the data over. And in this case, the source task will be like generating too many number of spills, and at the end of it, it has to do a final merge in terms of writing the data onto the disk. Only then the events will be sent to the reducer in terms of pulling the data. So we introduced the initial versions of the pipeline shuffle in the recent versions of Tez, wherein as and when a spill happens in the source task, an event is sent to the downstream vertex so that it can start pulling the data. So this has got two big benefits. One is you no longer need to do the final merge in the source task, in which case it's going to drastically reduce the amount of I/O that is required in the source. And the second benefit is, as and when the spill is getting generated, the downstream vertex is able to pull the data over and then merge it. So you're in a way overlapping the network along with the CPU. So in our internal benchmarks, we saw around 20% improvement for certain jobs which involve heavy skew. Just to give an example, in this particular DAG, map number 7 executed a single task, and it ended up generating huge amount of couple of GBs worth of data. So it ended up spilling lot many number of times, and finally it ended up doing a merge and generated somewhere around 11 GB of data. And it took almost like 925 seconds. And the downstream vertex, which is reducer number 7, was just waiting for the data to be generated from the source. With the pipeline shuffle, it took only 680 seconds. So that's a big improvement in terms of the overall runtime. And the biggest factor is you no longer need to do the final merge in the map number 7, which is going to drastically reduce the I/O cost. From the debuggability aspects, in the starting branch 0.6, there was a huge effort which has gone in terms of creating the Tez UI. In the earlier days, we used to debug the Tez, job problems by mining the logs that we obtained from the HDFS or so, which was a huge pain. So Tez UI, the source of truth for Tez UI is the ATS data which gets stored. So as and when the DAG gets executed, at the end of it, it publishes the data onto ATS, as Jeff pointed out. And Tez UI pulls the data from ATS and then renders that information. And this is going to be a lot more useful, not only for developers, but for admins as well as for the performance analyst. You can clearly look at the set of DAGs that are running in the system, the set of DAGs that ran on the system, and look at the various task attempts, the counters, and do all sorts of performance analysis on top of this. This was not possible in the earlier versions of Tez. And also, for debugging, we used to look at all the Tez logs in terms of analyzing what was the error that happened. But with the Tez UI, it becomes a lot more easier because the error automatically gets popped up in the UI. So it becomes a lot more easier in terms of debugging. One of the nice features about the Tez UI is that it is also possible to download the ATS data pertaining to a specific DAG by clicking the download data button. So this will be a lot more useful if you're trying to support remotely, where earlier we used to ask for all the logs, which is going to be in the, GBs or in terms of megabytes, but now you can ask for this particular download, you can ask only for this particular data and mine that information in terms of understanding what really happened in that particular DAG. The other feature that we added recently was the local mode, where you can create the Tez jobs and test it without having to spin up a Hadoop cluster. So you can, as long as you have an ID and you are able to write the Tez code, you'll be able to debug through your Tez code without having to deploy it on the Hadoop cluster itself. The only caveat is it will not go through the scheduler path or it will not go through the RPC mechanisms. Couple of questions that arises while debugging the production system is whether your containers got launched properly, whether they were pre-warmed properly, whether your containers got reused properly, were there any local reads or were there any remote reads that happened in the system, what are the kind of tasks that ran in the system, were they taking a lot longer time. So these are some of the questions that keep on coming up when you try to debug in the production systems. So we added the Tez swim lane, wherein you can look at most of this information by looking at the swim lane graph itself. For instance, this is a Tez session which had executed 4 different DAGs. And the first one represents the pre-warming session. The second one represents the remote reads, or the red color ones, the bars, which has got the red bars. They are the remote reads. And you can also look at the container reuses that happen in the system. We are also planning to incorporate a couple of other features, like when did the shuffle ended for a specific vertex? Did my reducer task take a lot longer time because the shuffle was running a lot more slower? So those set of details can be added to this particular graph by mining the data that we get from the download data button in the earlier slide that I showed. So whenever a job gets completed, the task attempt logs and all those details and the application server logs or app master logs, all of them get aggregated and then stored in the HDFS. So earlier, we were looking at it in a manual fashion sort of thing, but now we wrote a simple T-file parser, which will help in terms of parsing these T-files without having to modify any of the things, and it lets you do the parsing in the pig itself. So in a way, we are analyzing the Tez log using Hadoop itself. So this graph represents one of the analysis that we did based on that particular analysis. For instance, the y-axis represents the source machine, the x-axis represents the destination machine, and the z-axis represents the time taken for the download. So in this case, as you can clearly see, any data which is downloaded from machine number 7 to any of the other machine has taken a lot longer time when compared to the other machines. So this sort of analysis helps a lot in terms of identifying some of the slow nodes in the cluster, which I have got excuse me, which have got some network issues. However, it is not limited to this particular thing. If you have a custom processor and if you have enough logging added to the processes or so, you can also make use of the parser and do some analysis on top of it. Additional analysis that could be done are, something like this, where you try to analyze the amount of data that got transferred from the source to the destination. So this will help in terms of identifying whether there were any skews available in the system or not. So from the roadmap perspective, we are planning to add the shared output edges where the same output can be given to the different vertices. And we are planning to have local mode stabilization. Currently in the local mode, we are able to execute only one task, but we are planning to add more number of tasks. And we are also planning to optimize the runtime, wherein you'll be able to add the vertex at, or add or remove the vertices at runtime. And we are also planning to add a partial completion vertex manager. For instance, currently the tasks within the same vertex cannot talk to each other, but it might be useful to have this kind of communication possible for certain scenarios. For instance, let's say you have a select query with a condition and limit by 10 or so. As and when the 10 records are generated, you might want to stop the other tasks that are running in a graceful fashion. So to mitigate that, we need to have the partial completion vertex manager. We're planning to add that. Co-scheduling is something like if you're able to start the producer as well as the consumer at the same time, then instead of writing onto the disk, you can directly stream through the data onto the downstream vertex. And also we are planning to add a lot of framework stats in terms of making better runtime decisions. From the adoption perspective, Hive has been using Tez for quite a number of releases, and Pig has been using Tez starting 0.14 release. There are a couple of other projects which make use of Tez, for instance, cascading as well as Flink. These are some of the useful links in terms of understanding the community. For instance, you have Jira links, code repository, and dev, user, and issues list. That's pretty much it, and we are open for questions.
So my question is, what's the comparison between Tez and Spark? What's the comparison between Tez and Spark? As far as I understand, the major features of Tez, like DAGs, like storing data in memory, and even sharing right now data across RTDs exist in Spark. What's the niche of Tez, considering that Spark is very trendy right now and obviously outnumbered by the number of committers?
Okay, yeah, so actually Tez and Spark are for two different purposes. The Spark is on the application layer, so usually you use Spark to solve your application problem, and the Tez is on the execution engine layer. So usually you use Tez to build an execution engine, and on the you can see the difference between the on the API between the Spark and the Tez. The Spark exposes the API or RDD, and you can do some operation on the RDD, map, reduce, group by, something like that. But for the Tez, you can see the API is for build the DAG and how to optimize the execution. You can see that in Tez, we can specify the input, output, and process. We can specify how to read that and how to write that. And we can also do the dynamic parallelism estimation. So, but for Spark, there's no API for that. So actually, these two things are on different layers, although they have some common things. Yeah. Hope that answers your question.
Yes, answers, and no, not answers. Let me maybe formulate a little bit different. As an end user, I really do not care is one tool or framework exists on the execution layer and another on the application layer. I'm solving a particular task. For instance, to speed up my query or speed up my machine learning job. And the rest for me is transparent. And what I'm just trying to say is, what's the benefit for me to type hive.execution engine equal Tez instead of calling Spark, or in Spark, in Hive 1.1, use the Spark as an execution engine?
Okay, so your question is how to decide use underlying execution when use Hive, use Tez or Spark?
That's correct. And also,
Okay.
what's the benefits of
Okay.
Tez over Spark?
Okay, so actually, for now, I think that at least the scalability of the test is much better. And actually, from the beginning, the Hive used the MapReduce for this execution engine, and now actually many of the stuff in the test we borrow idea from the MapReduce, and we try to make it 100 compatible with the MapReduce. So we try to do everything that MapReduce can do. Tez can do that, but Tez can also do a lot of other things that MapReduce cannot do. And for this Spark, Hive on Spark, as far as I know, it's still not versional, but and there's still some scalability problem on that. I think maybe 1 or 2 years later, it will become better. Yeah.
So just to add to that, Hive on Spark just started recently, and in the case of Tez, there are a couple of additional features, like you have custom vertex managers that can be added. Hive is already making use of that. For instance, for doing the dynamic partition pruning, they're making use of the custom vertex manager in Tez in terms of doing it in a better fashion. So those set of features may not be available in Hive on Spark. So that's one of the added points.
I have a question concerning one of the slides. Can you please go to the previous slide concerning building a histogram, where you had this small pig job?
This
I think it was towards the beginning, second. No. I think,
Jeff's slide?
yeah. It's your
Oh, the pig example?
the pig
Order by
yeah.
example. Okay.
So I remember you mentioned that there are 2 MapReduce jobs for ordering.
Yeah. So this
Yeah,
slide.
yeah, exactly, this one. So if I understood it well, so there are 2 MapReduce jobs for this order to sort this, key by X. Why not having one taking advantage of the shuffle and order part? Do you see my question? Okay.
I'm not sure. So, what's
Is it correct that 2 MapReduce jobs will be running here to execute the order by?
Yeah.
Why not one? Yeah.
So in MapReduce, you cannot have multiple outputs. So you need multiple outputs from one stage for that to work. So map and reduce, you can only have a pair of things connected by single edge. So
it can take advantage of the internal mechanism of shuffle and order?
the shuffle and order only lets you do that after you partition. So first you have to generate your partition order, which says 0 to 100 is the first partition, 100 to 200. If you have random data, you don't know where to partition. You want each reducer to get uniform data chunks. So you generate a histogram, equal height, and then chop it up and sort them individually.
In the last slide, you mentioned also, or I think the previous, before the last, you also mentioned Apache Flink. How do you see the relationship between Flink and Tez? Do you see Flink more like an application layer that uses Tez as an execution engine, or
That's right.
Yeah.
That's right. Yeah.
Hi, you talked about the pipeline shuffle path.
Yeah.
Are you saying therefore that you can repartition the data set in a pipeline without landing the records on disk? Is that what you're saying?
Can you please repeat the question?
Are you saying you can repartition the data set without, in the pipeline without landing the records on disk? Is that what you're saying?
No, it still ends up writing the data onto the disk, but you don't need to have the final merge. So in the earlier versions of Tez, what used to happen is when multiple spills are happening, at the end of it, it used to have a final merge where you used to merge all the spills together and then write a final merge in the source. Only when that particular piece was done, it used to send an event to the downstream vertices stating that, hey, you can consume the data. So with the pipeline shuffle, we are completely avoiding the final merge step that is going to happen. So as and when a spill happens in the disk, it is going to send an event to the downstream vertex to consume that particular spill.
Could we imagine Spark running over Tez?
Sorry, can you repeat that question?
Could we imagine that Spark could be running over Tez?
Sorry, I didn't understand.
I was asking if, because Spark is using his own DAG scheduling, and maybe it could use Tez as well.
Spark on Tez? Oh, okay. Yeah, so there was an effort in terms of porting or like running Spark on top of Tez. So that's an internal effort, but I'm not too sure whether we are planning to open source it or not. Oh, okay. But we put up the patches, but they were not active. Oh, okay. Okay.